Hello, everyone. And today's non-class learning will look at the second episode of Pain, Pus, and Poison. We skip pus. Believe me, that's the best for the both of us. And we're going to be looking at poison today in the following lecture. Okay, here we go. Turn off this.
This is Walton Hall in Yorkshire. In 1835, it was home to a wealthy and somewhat eccentric gentleman.
It's said he could be seen regularly walking the grounds barefooted and in the company of an aging donkey. Now, they must have been a pretty shabby pair, but between them they took part in one of the more extraordinary experiments of the 19th century. An experiment that would lead to significant breakthroughs in medicine and in surgery and would transform our understanding of poisons. Go on then.
Pain, Pus and Poison has charted the many colourful characters who, over the past 200 years, created the medicines which protect us from pain, infectious disease and even death. Through their heroic efforts, chemicals, almost magical in their effects, were discovered, scrutinised and finally exploited. In this programme, I'll reveal the remarkable science behind perhaps the most unexpected source of many modern medicines: poisons. Poisons that include the planet's most deadly substances.
A couple of kilos would kill every human on the planet.
From the natural world to the man-made, it's a tale of greed, tragedy, hope, and chance.
What started out as a science expedition looking at bugs turns into a cancer therapy. To me, I think that's one of the wonders of science.
So, just how far can we go into unlocking the benefits of poisons?
All medicines are poisons, and all poisons should be considered as potential medicines.
This is the story of how we have turned killers into cures.
Poisons have, throughout history, been used to take life, whether by suicide, assassination, or murder. And yet, until the 19th century, surprisingly little was known about how they actually work. Someone who helped change that was Charles Waterton, the colourful squire of Walton Hall.
He was considered very eccentric. He used to sometimes hide under tables and bite people's legs at the dinner table. He was double-jointed. He could scratch behind his ear with his big toe. He was an avid tree climber. He climbed trees into his 80s. That's quite strange.
As well as being an eccentric, Waterton was also a man with a passion for knowledge. He travelled the globe, collecting the exotic and the unusual. Not always simply for scientific study.
He created a taxidermy piece after a customs officer had upset him by charging extra duty on the specimens he brought back from Guyana. He changed the rear end, the arse of a howler monkey, to look like this customs officer's face, which is possibly the perfect insult.
Waterton spent nearly 20 years living in the Amazonian rainforest, where he befriended one of the Amerindian tribes called the Makuzi.
Now, what Waterton was really interested in was a closely guarded secret, a poison that could kill almost any animal and which occasion they used to kill each other. He managed to get the recipe from the Indians. It's got some really interesting ingredients. We've got the fangs of the labari snake, and there's also apparently some black ants you pound in, which are so venomous their sting alone produces a fever. But it's actually not those things. The key ingredient is a vine which grows in these wilds, which is called wurali. It is from this that the poison takes its name, and this is the principal ingredient.
This vine was later identified as Strychnos toxifera, and the poison from it is known today as curare.
Now, these are real samples that Waterton brought back 200 years ago. A bowl in which you'd sort of mix up the ingredients, and these are the poison darts. In fact, the poison is the black stuff on the end. That is curare, and although it is 200 years old, it's still active, so I'm not going to touch it. Now, Waterton himself brought it back because Europeans were absolutely fascinated by curare, and no one else had succeeded in getting the really good stuff in quantities, certainly not enough to do proper experiments with.
Back home, Waterton was approached by leading vet Professor William Sewell and eminent surgeon Sir Benjamin Brodie, who wanted to find out exactly how curare killed its victims. Brodie had already tested the poison on small animals, but now wanted to experiment on something larger. So they used a donkey. They injected the unfortunate donkey with enough curare to kill it. Then, when it collapsed and stopped breathing, they quickly performed an emergency tracheotomy.
What you do is you get a knife and you slit your way into the windpipe here. And then what they did is they inserted a pair of bellows into the windpipe and pumped away. And they really had very little idea of what they were doing. They didn't know how long they would have to do it for. After about 2 hours, the donkey sort of recovered enough to look up and sort of stare at them. So they stopped, and the donkey then collapsed. So back to the bellows again. They kept this up in total for about 4 hours, until finally, as Waterton wrote in his journal, the pumping had saved her from a final dissolution. She rose, she walked about without obvious agitation or pain. Yes.
Waterton, Sewell, Brodie, and of course the donkey, had demonstrated something remarkable. A discovery that would have an unexpected and far-reaching impact. They had shown that curare acts on specific muscles, including those that enable you to move and breathe. Whereas other muscles, including, crucially, the heart, were completely unaffected. As long as you can keep the patient breathing, he, she, or it should survive.
The key aspect of curare is that it's a muscle relaxant. All your voluntary muscles will stop working, including the respiratory muscles.
The three scientists had shown it's possible to keep a patient alive while their body is rendered immobile, relaxed by curare. Now, in the early 1800s, this discovery had no obvious application, but 100 years later, it would transform surgery.
In the mid-20th century, one of my favourite self-experimenters, Dr. Fred Prescott, deliberately injected himself with a pure form of curare to demonstrate that it is safe to use as a form of muscle relaxant in surgery. In fact, since the 1950s, most people who've had major surgery will have benefited from curare or one of its modern equivalents.
And the donkey? She was retired to Walton Hall. Charles Waterton wrote in his diaries, "She shall be sheltered from the wintry storm, and in summer she shall have the finest pasture. She will end her days in peace." In fact, she did live another 25 years, and when she finally died in 1839, she got her own obituary in the local paper, detailing her contribution to medical science. Victorian Britain, life was harsh and often cut short. Life insurance suddenly became a boom industry. This led to a surge in financially motivated murders, many by poison. These poisonings would in turn have unexpected consequences for pharmacy and forensic science. One of the most high-profile Victorian cases was a woman called Mary Ann Cotton.
She was married 4 times. 3 of her husbands, heavily insured, all died. The one who survived seems to have done so because he refused to take out insurance, so she left him.
In all, 10 of her children died of what appeared to be gastric-related illnesses. Tragic and terribly sad, but fortunately, most of them were insured.
Her mother, her sister-in-law, and her lover also died, and in each case, she benefited. By 1872, the unfortunate Mary Ann had lost an astonishing 16 close friends or family members, but there was one left, her 7-year-old stepson, Charles Cotton. Now, she tried to give him away to the local workhouse, but they wouldn't have him without her. Young Charles soon died. The manager of the workhouse, however, got suspicious when he heard about the death of the child, and he contacted the police. They investigated and exhumed the body of young Charles.
They suspected foul play and, not surprisingly, wondered if Mary Ann had poisoned him. They thought they knew how she'd done it. With arsenic.
Arsenic was an excellent way to kill somebody. It's known as a cumulative poison, which means that you don't excrete the dose. So in other words, the more you take, it builds up more and more in the body. And it was very easy to administer in the food. So it just looked like somebody was dying of natural causes.
The trial of Mary Ann Cotton would hinge on whether they could find traces of arsenic in the body of Charles Cotton. Now, forensic science was still in its infancy, but they did have a good test for arsenic. The reason for that is there was an awful lot of arsenic poisoning around.
This test is called the Reinsch test, and it was the one used to discover whether Mary Ann had poisoned little Charles. A sample from the boy's stomach and intestines was heated with acid and copper. If arsenic was present, the copper would turn dark grey, and when placed on paper soaked in mercury bromide, produce a telltale yellowy brown stain.
And when they did this test on the body of poor little Charles, they discovered that he had indeed died of a lethal dose of arsenic. His stepmother, Mary Ann, was convicted of his murder on the basis of this, and she was hanged in Durham jail in March 1873. She was never taken to trial for the mysterious deaths of her mother, 3 husbands, 2 friends, and 10 other children.
Throughout the 19th century, tales of sinister poisoners and unfortunate accidents filled the newspapers. And it was because arsenic was such a silent and prolific killer that some of the earliest techniques in forensic science were developed. But arsenic was about to do more than that. It was about to shape the development of the modern drug industry.
Now, I'm feeling quite nervous because this stuff is really, really nasty. It actually is a mineral, and even a tiny, tiny amount, less than 1/100 of an ounce, would kill you. As a poison, it is almost unrivaled because it's completely tasteless, dissolves in hot water, and it takes so little to kill. I'm going to put that back in there, and then, go and wash my hands.
Arsenic trioxide was marketed as a rat poison. It was cheap and easily available. Children would blithely collect it from the shops, along with tea, sugar and dried fruits. A fact satirized in this Punch cartoon from 1849. And yet there was clear evidence of it being used to murder people. So pressure was growing to bring this deadly poison under some sort of control.
The Pharmaceutical Society, along with what became the British Medical Association, got together in 1849, went to Parliament and lobbied for a new law to actually stop these poisonings. As a consequence, the new act was passed, which is the 1851 Arsenic Act, which greatly restricted the sales of arsenic.
The new act said that if you were selling arsenic over the counter, then you had to keep a record. You also had to know the person you were selling it to. And finally, in future, all arsenic would have to be coloured with soot or indigo. So presumably if your husband or wife was trying to poison you, then you had a better chance of detecting it.
It had even been proposed that women should be banned from buying arsenic. But that measure didn't make it onto the statute book. Although the Act restricted who could buy arsenic, it made no mention of who could sell it. So inevitably, the deaths continued. A few years and many murders later, Parliament finally introduced further laws to restrict the sale of the more obvious poisons. More importantly, they also created the trade of chemists and druggists.
The Arsenic Act and other acts that followed finally brought arsenic and a whole range of other dangerous chemicals under some sort of control. Now, I do think it is gloriously ironic that it was from all these poisonings, accidents and murders that the modern legitimate business of pharmacy emerged.
At the start of the 19th century, poisons had been mysterious and deadly compounds, convenient for killing yourself or others. By the middle of the century, a more rational understanding of how they worked was emerging. And, along with a legal and professional framework designed to control their use, it would lead to a new era of scientific discovery.
This is belladonna, deadly nightshade, and there is certainly enough there to kill me. Now, belladonna in Italian means beautiful lady. And that's because in the past, elegant ladies would get the juice from this plant and they would use it to dilate their pupils in the hope that it would make them look more attractive. In the 19th century, they managed to isolate the active ingredient from the belladonna plant. It's a substance called atropine, and ophthalmologists started to use this to help them examine the eye. Now, I have the modern equivalent here, and I'm going to put some in my eye to see what happens. Oh, God, that does sting. Over the last few minutes, the focus in this eye has gradually gone. And I think you can tell that my pupil is a great deal bigger in this eye than that eye. But am I more attractive? One of the reasons why having a big pupil is supposed to make you look more attractive is because when you look at somebody and you find them sexually attractive, then your pupils expand. So it's really just me saying to you at this moment, I find you very, very attractive. And that's why you find me very, very attractive.
Atropine is extremely toxic, and ladies dying to look more beautiful were at risk of doing just that. And yet, oddly enough, the best treatment for atropine overdose turned out to be another poison.
In 1864, in Prague, a doctor was summoned to treat 4 prisoners, who had broken into a local dispensary and, thinking they were drinking alcohol, had drunk a large quantity of liquid containing atropine. When the doctor got there, they had clear signs of atropine poisoning. The men were seriously ill, lying prostrate on the ground, vomiting profusely, with these huge dilated eyes. The doctor had no idea how to treat them.
Then an ophthalmologist friend of his suggested something radical: poison the men even further. But this time with a different poison: extract of calabar bean.
Calabar beans contain a number of pharmacologically active alkaloids, one of which is phytostigmine, which constricts the pupils, unlike atropine, which dilates them.
The hope was it could also reverse the other more serious effects of atropine.
The doctor felt he had nothing to lose. So he took the man who was sickest, whose temperature had gone up and who really looked as though he was on the brink of death, and he got him, not without difficulty, to consume some of this second poison. Within a few hours, his temperature had come down. Within a day, he was completely cured.
Calabar beans and atropine have opposing actions. They can be used to cancel each other out. So effectively one can be used as the antidote to the other, either way around.
And it wasn't long before poisons began to be commonplace in a physician's drug cabinet. In fact, these days, atropine is often used to reverse the effects of insecticide poisoning, and is also used to treat some forms of heart disease.
During the 19th century, researchers looking into poisons were on the whole trying to find ways to make them more productive, more beneficial. At the start of the 20th century, things took an altogether bleaker, darker turn.
World War I. It would leave 17 million people dead or missing in action. It was a living hell. And it was made even more hellish by the work of industrial chemists.
In July 1917, troops based in Ypres, Belgium, reported a strange peppery smell in the air and a golden shimmering cloud that surrounded their feet. Within 24 hours, they had started to itch uncontrollably, and they came up in horrible, painful blisters and vile, incurable sores. Those who had inhaled too deeply started to cough up blood.
Okay, and so we've been building up to this moment. Oh, sorry about the cream. I got just went in the sun for too long. In this case, I pause here because, of course, we are going to discuss chemical weapons in the class. Of course, to eventually get us to biological weapons, one had to be invented first. The first was the biological weapon. I'm sorry, the first was the chemical weapon and then the biological weapon. Now, what did he describe? The blistering, right? And that's the thing you have to understand about the first chemical weapons. First, there was chlorine. Now he's going to be talking about a new type of chemical weapon. Both of those chemical weapons are called blister agents because literally what do they cause? Both blistering on the outside of your body and on the inside. Now, when blistering happens on the inside of your lungs, okay, it's going to have fatal consequences.
Blood. The troops had been poisoned by mustard gas.
Gas masks like this one were state-of-the-art at the time, but they were pretty useless against mustard gas. The problem is, mustard gas can be absorbed through the skin. Even if you were fully clothed, you were not fully protected.
So he's talking about the Battle of Ypres in 1917. In 1915, during the Battle of the Somme, that was the first time a weapon of mass destruction was introduced. That was chlorine gas. Okay. So in other words, as a result of the Germans deploying chlorine gas, what was now standard issue for any soldier during World War I, the gas mask, okay? So then why was mustard gas developed? Well, as a means of overcoming the protections that the soldiers had. In terms of their gas mask, you had to create a blister agent, even deadlier.
Gasping, spluttering, drowning. It could take up to 6 weeks to die, and it was a terrible death. Now, mustard gas was not the first of the poison gases. It was actually one of a number that had been weaponized by the Kaiser Wilhelm Institute under the directorship of a man called Fritz Haber. Fritz Haber was a professor at the prestigious University of Karlsruhe and was married to fellow chemist Clara Immerwahr. Haber would go on to win a Nobel Prize in chemistry, but he also played a major role in the manufacture of chemical weapons.
He really pressed the Germans, who the German military didn't have much regard for science, pressed the Germans to see what science could do in providing them with explosives and in providing them with chemical weapons, and he oversaw the first use of chemical warfare on the Western Front.
He saw it as an efficient way to fight a war, and he didn't think it was especially inhumane. After all, he said, death is death, however it is inflicted. His wife, Clara, pleaded with him to stop working on gas warfare. He angrily and publicly denounced her as a traitor. Gas warfare was a horrific but extremely effective new weapon. It not only crippled and killed, but also instilled terror right across the battlefield.
Casualties from the first use at April were estimated at 5,000 to 10,000 dead, with many, many more injured. And Haber was delighted, as were the German military.
Haber was promoted to captain and he returned to Berlin in triumph. But the couple continued to argue because Clara was deeply unhappy with what he was doing. Haber, however, felt that he had an absolute scientific and patriotic duty to continue working in chemical warfare. Finally, and tragically, Clara took matters into her own hands. In the middle of the night, Clara silently removed her husband's pistol from its holster. She stepped outside, and then she shot herself through the heart. Later that day, Fritz Haber left for the Eastern Front to oversee the next gas release against the Russians. He left behind his grieving 13-year-old son, who had been the one to discover his mother's dead body. Haber continued to enthusiastically promote the use of poison gas, and his colleagues would go on to develop even more deadly nerve gases. One reason why World War I became known as the Chemist War. But the story of mustard gas does not end here. 20 years later,
something I want to just interject that the documentary skipped over. Farber was actually a colleague of Albert Einstein. Farber's wife, Immerwahr, she was Jewish. And this is kind of a sick, well, I'll tell you what's going on. And it's an awful thing to say, but perhaps maybe she was fortunate to kill herself, because if she only knew what Farber's invention would evolve into. You see, why am I dealing with chemical weapons? Well, like I said, they're a precursor to biological weapons. But Farber's invention of using poisons against people would evolve into something very nefarious. Instead of deploying gas through a cannon, what if you could concentrate this poisonous gas into a pill called Zyklon B? Okay, and Zyklon B is a chemical weapon. It would be deployed in gaseous form, but not through battlefield cannons, but through shower systems during the Holocaust. In other words, Farber's invention is going to take us to its most brutal apotheosis in the Holocaust, the gas showers. Okay, that's their evolution. Now, oh gosh, sorry about this. Anyway, now we kind of come into a vicious full circle. How were the mass victim of the gas chambers in, let's say, a place like Auschwitz tricked going into the showers? What were they told? They were going into showers to be deloused, okay? Because around this time, a major disease that was spread by lice, and it was called typhus. In other words, that is not only the cruel trick they used on the Jewish victims to convince them to go into the gas chambers, but now you also have to understand the Nazi mentality behind this. Okay? You see, just as these chemicals were used to kill lice in real life, the Germans literally considered the killing of Jews during the Holocaust as a delousing process. In other words, the killing of lice. They saw these human beings as lice. Okay. In other words, I want you to understand that the German approach to disease and the mentality it created, in a lot of ways, brought us to the Holocaust. Anyway, ask about this in class if you want further clarification.
With World War II looming, researchers at Yale University School of Medicine retreated to their labs to try and create antidotes to mustard gas. They feared a repeat of World War I. But what they discovered would lead them into a very different kind of battle. Two of the doctors involved were Louis Goodman and Alfred Gilman. Working in these libraries, they delved into the medical records of soldiers who had been exposed to mustard gas in the First World War. And what they found, amongst other things, was that these soldiers had surprisingly low white blood cell count. This chance discovery would lead to a radically new treatment for one of our greatest killers, cancer. Cancer occurs as a result of mutations in a cell's DNA. These genetic mutations either promote excess cell growth or remove the normal safeguards that limit cell division. Either way, the cell begins to divide uncontrollably. One type of cell that is particularly prone to mutation is the leukocyte, or white blood cell. Goodman and Gilman thought to themselves, if mustard gas can destroy normal white cells, perhaps it can also destroy malignant ones. It was certainly worth a go. After successful animal trials, they looked for a human volunteer with white blood cell cancer to test their theories on. They found a patient with advanced lymphoma, known to us only by his initials, J.D. These are J.D.'s original medical notes, which were lost for nearly 70 years. And I'm the first person outside the Yale medical community to lay my hands on them. They tell a fascinating and poignant story. J.D. was a Polish immigrant in his 40s, a metal worker. He was riddled with cancer and had a massive tumor on his jaw.
When he first came in, the tumor had progressed to the point where he could not swallow, he could not sleep at night, he could not fold his arms across his chest because the lymph nodes and cancer under his arms was so massive, and he was really encased front and back by tumor and up to his face, and he was just absolutely miserable.
His doctors tried everything they could, but the prognosis was not good. They had a case conference and concluded it with this line: "The patient's outlook is utterly hopeless on the present regimen." With nowhere else to turn, J.D. agreed to try the experimental drug based on deadly mustard gas. The notes say that at 10 a.m. on the 27th of August 1942, they gave him the first injection, what they call synthetic lymphocidal chemical, but which was in fact nitrogen mustard. Because of the war, even JD's treatment was a secret. They couldn't name nitrogen mustard. In the records, it was simply called Substance X. X given at 4:30 p.m. and then again X given at 9:30 a.m. the following morning.
He received a number of treatments using nitrogen mustard, and with each one he became a little bit better. He could actually sleep at night, he could swallow, he could eat, he was much more comfortable, the pain became minimal, and he was absolutely thrilled.
Although not fully understood at the time, nitrogen mustard works by binding to the DNA of dividing cells. This triggers the cell's self-destruct mechanism. Instead of dividing, the cells shut down and break apart, and the cancer, hopefully, is destroyed. This was the first time that a drug had been used to treat cancer. This was monumental. I mean, it was a huge moment in the history of medicine. It is the beginnings of what we now call chemotherapy. And very strange to think that it all started in the horrors of the trenches of the First World War. All the chemo drugs that followed have had the same basic mechanism of action. They are poisonous to living cells. If you get the dosing right, then you can kill the cancer without killing the patient. And in fact, nitrogen mustard is still used for the treatment of some cancers. But cancers are persistent. Even today, the prospect for people with advanced cancers is often poor. For JD, treatment came too late.
To say that he enjoyed a few months is probably accurate, but ultimately he followed a downhill course.
JD, the world's first chemotherapy patient, survived for 6 months. There's just one entry for the 1st of December 1942. It simply says, died. JD died peacefully, unaware of the impact his life and death would have.
His story pulls the strings of your heart. It really does. And I think that he was a sad person with few friends with a devastating disease. And he made a huge contribution to management of cancer. So we are grateful to him for that. And we share his agony at the same time.
The field of chemotherapy, and indeed the very idea of using poisons as medicines, poses fundamental questions about toxicity. How do you decide which substances are poisonous and which are not? After all, even the ancients realized that poisonous is a relative term. All substances are poisonous. There is none that is not poisonous. Now that's according to 16th century doctor and chemist Paracelsus. He goes on to add, it is simply the dose which determines whether a substance is poisonous or not. Even water can be lethal if you drink enough of it. Too much causes brain cells to swell, which can lead to coma and death. So how much water would I have to drink for it to kill me? About 7 litres, drunk over a few hours. That would leave me with a 50-50 chance of surviving. And when it comes to coffee, about 100 would probably finish me off.
And it's not just the amount that matters. The toxicity of a substance can depend on what species you are.
Now, I absolutely love chocolate. If I were to eat a bar this big...
So speaking of poisons, you see there is one plant that has a natural pesticide built in. And that plant, that pesticide, what it does is when a bug munches on it, it dies. Okay? Because for the insect, the amount of that poison is enough to kill it. For us humans, on the other hand, we consider that poison heaven. Okay? I'm not sure if I said this in previous lecture, but probably I did. I love telling the story. Of course, yes, that poison in that plant, we know it as caffeine. Okay? The coffee bean has its own, that's what it's saying, drink a lot of caffeine. And then you're going to give yourself such a dose that the little dose that kills an insect, you've given yourself such a big dose that it kills you. Something to think about when you're doing your all-nighter. Hopefully not for the paper for this class. That'd be tragic. No.
Then it would probably make me feel a little bit queasy, but nothing worse. However, it would be a very different story if I was a dog like Dolly here, because chocolate is very bad for dogs. 2 bars this size on a dog this size could well be lethal. The thing is, it contains a substance called theobromine, and theobromine in dogs causes vomiting, heart problems, and convulsions. So this is for me and not for you.
Toxicity also varies according to the type of exposure, whether the poison just touches the skin or is inhaled, ingested, or even injected. Nonetheless, it is extremely useful to have a comparative scale of how toxic various substances are.
One measure of lethality is the LD50, the lethal dose 50%. In other words, how much of a substance would kill half of these mice?
Although now rarely tested on rodents, the concept of LD50 has stuck. To allow for size, doses are given per kilogram of body mass. On a standardized LD50 scale, water comes in at greater than 90,000 milligrams per kilogram of body mass. Pure alcohol is fatal to half the population at 7,000 milligrams per kilogram, while caffeine weighs in at 192. Arsenic has an LD50 of 14. Curare is lethal at only 0.5. So while anything can be poisonous, substances with an LD50 less than 100 milligrams per kilogram tend to be called poisons.
On this scale, most chemotherapy agents, including nitrogen mustard, would register between 1 and 4 milligrams per kilogram.
By the 1950s, researchers had turned some poisons into effective drugs. Natural plant poisons like curare were being used in surgery, and synthetics like nitrogen mustard were having an impact on cancer. They were just a small part of a new enthusiasm for pharmaceutical products. But in this dash for cash, the authorities overlooked the fact that while poisons can be medicines, medicines can also be poisons. It was only a matter of time before something went badly wrong. Amongst those rushing out new drugs was a German company called Chemie Grunenthal.
Staffed by many former Nazis, they were searching for lucrative new medicines and had created a chemical that looked particularly interesting. Structurally, the drug was very similar to barbiturates, a class of drug that was then widely being used for anyone who had a sleep disorder. So the company decided to send it off to doctors and get them to try it on their patients who had sleeping problems. The new drug did well and was soon being heavily marketed as effective against insomnia, coughs, colds and headaches.
Oddly enough, I mean, it was a sedative, but it was also known to be quite useful in morning sickness for pregnant women.
It was distributed initially under the brand name Distaval. By 1960, Distaval was sold throughout Europe, South America, Africa, Canada, and Australia. Around this time, the number of babies being born with deformed or missing limbs and organs, well, they started to rise. Initially just a few, but then the numbers took off. Now, this was clearly really distressing, and something was going on. The problem was the doctors didn't have a clue what. Several traumatic years passed before the cause was finally found, when a young Australian doctor looked at the mothers rather than the babies. The only thing he could find was that these women had all suffered from morning sickness in the early months of their pregnancy, and they had all been prescribed the drug Distaval, which is now more commonly known by its generic name, thalidomide. It has been estimated that around 10,000 babies were severely disabled by thalidomide, half of whom failed to live to adulthood. The situation in America, however, was very different. It was 1960, the year before the link between thalidomide and birth defects would be made. Frances Kelsey was just starting out a new job at the Food and Drug Administration. Her first assignment was to review an application to market thalidomide. Since it was already on sale in the rest of the world, and since no one yet knew that it caused birth defects, it should have been a case of simply approving it. But Kelsey strongly felt the application was not up to standard.
Here's a person who was very well trained in pharmacology and medical practice. And so when she saw the application, she was kind of appalled. It struck her more as testimonials than good, solid clinical research. And she sent a letter responding to the application saying that in its present form, it could not be accepted and to submit additional data.
Another application was submitted to the FDA. But Kelsey was still not convinced by the safety data. So despite mounting pressure from the manufacturer, she again refused thalidomide a license.
There was a back and forth between FDA and the Merrill Company. The Merrill Company was getting quite annoyed, honestly, threatening to go to not only the supervisor, the head of the Bureau of Medicine, but the commissioner of FDA. But she stood her ground. She stood her ground as a scientist. She stood her ground as an FDA official who was, of course, had to uphold the law, and the law required that the drug had to be safe. She persevered through this whole process.
Kelsey continually refused to allow thalidomide a license. When in 1961 the facts finally came out, Americans appreciated just how close they had come to sharing in what was by then a worldwide tragedy. Frances Kelsey was given an award by John F. Kennedy in recognition of her outstanding work. Thalidomide was eventually withdrawn from the worldwide market. The fact that this tragedy was allowed to happen and go on for so long emphasizes how little control many governments actually had over medicines just 50 years ago. In Britain, for example, the Arsenic Act and the acts that followed it had put existing drugs and chemicals under some sort of control. But there was still no effective regulation of newly discovered drugs. After the thalidomide scandal, new laws were passed here and in other countries, which meant that in future, drugs had to be safe, they had to be effective, and doctors also had to tell their patients if they were being given something experimental. Because astonishingly enough, before then, a doctor could give you pretty much what he or she wanted, and they didn't have to tell you. These days, pharmaceutical companies wishing to launch a new drug have to go through multiple clinical trials to demonstrate that their drug is safe and effective. It can take years and cost billions of pounds. But it's only by doing this sort of rigorous testing that you discover if a drug has significant toxic side effects.
The broader impact of thalidomide, it essentially creates eventually a gold standard for how drugs should be evaluated.
Thalidomide led to much tighter regulations, which was a good thing. But the story of thalidomide does not end here. Thalidomide seems to cause birth defects by blocking the creation of new blood vessels. Growing limbs are particularly vulnerable. It is clearly a very dangerous drug. Yet this notorious chemical has been found to have beneficial effects. For example, when it was given to people with leprosy, their skin lesions turned from this to this, literally overnight. And it's also being successfully used on a particularly hard-to-treat form of cancer, multiple.
And of course, you remember with leprosy, we dealt with that in the previous lecture. One of the most endemic conditions, along with smallpox and malaria. One of the most endemic afflictions in human history. Think in the Bible, how much references there are to leprosy, Jesus healing the lepers, so on and so forth. Of course, by this time, we didn't have, in the 20th century, no Jesus touching people and healing them. Thalidomide became kind of the 20th century Jesus, for the lack of a better term.
Myeloma. The rise and fall and rise again of thalidomide illustrates just how tricky medical research can be. In one context, a drug can be a poison. In another, a lifesaver. Despite the challenges, and with tighter regulations in place, medical research continues apace. While some still focus on mineral and plant poisons or build synthetic ones, others are now driving forward into the dangerous world of the microbe. Although they are only microscopic, microbes can produce toxins which are real heavyweights. And the ultimate microbial poison we have purified and tamed is a toxin produced by the microbe Clostridium botulinum. Botulinum toxin is the most poisonous substance known to man. Now, a couple of teaspoons.
Okay, this sounds really weird, but this is my most favorite poison. Now, keep in mind, before we get into this, botulinum toxin. This is now no longer a chemical poison. This is biological. And this is what I'm saying, how chemical weapons led to the evolution of biological weapons. Here it begins, botulinum toxin, okay? Now, every single one of you has heard of this toxin. You've just heard of it through its abbreviated name. But this is the most common biological weapon in the world.
Would be enough to wipe out every person in the UK. And a couple of kilos would kill every human on the planet. Fortunately, this is sugar. But I do have some botulinum toxin, better known as Botox, over here. Only a
What did I say? Every single one of you has heard of this biological weapon. You know it as Botox. Botox is a biological weapon. Okay. When people are using it for cosmetic purposes, they're taking what is a biological weapon and just injecting a small dose. Okay. But you see how deadly it is in large doses.
A few nanograms, but it is botulinum toxin nonetheless. The toxin is produced by bacteria and was first discovered in poorly prepared sausages during the 18th century. It was named after the Latin for sausage, botulus. On the LD50 toxicity scale, Botox measures just 0.0000001 milligrams per kilogram, the deadliest of the deadly. A lethal dose for me weighs less than 1 cubic millimeter of air. Botulinum toxin, like curare, commonly kills its victims by causing respiratory failure. But unlike curare, you're not going to be able to keep someone alive with a pair of bellows, because botulinum toxin lasts much longer. You have to keep them on a ventilator for weeks, if not months. Botox works by preventing muscles from receiving nerve signals. Botox is an enzyme which enters the nerve and destroys vital proteins. This stops the communication between nerves and muscles. Only the growth of new nerve endings can restore muscle function, and this can take months. Botox is a neurotoxin, which means it destroys nerves. Now, oddly enough, that makes it useful for a number of medical conditions, ranging from eye squints to migraines, from excess sweating to leaky bladders. But its main use, of course, is ironing out wrinkles in aging faces. And it does this by destroying the nerves that cause frowning. The quantities used are absolutely tiny. A few billionths of a gram dissolved in saline. In the name of science, I tried Botox a few years ago.
Wasn't painful, was it?
No.
It certainly smoothed away the wrinkles, but it also gave me a weird expression until the new nerve endings grew back. It may not be to everyone's taste, but Botox is certainly big business. Costing around £100 trillion per kilo, Botox is the most expensive product on Earth. Huge amounts of money can clearly be made from new medicines, so it's no wonder that the search for them continues. Having started out by collecting exotic poisons extracted from plants, such as curare, we've come full circle. As well as microscopic life, researchers are intensely interested in studying some of the other ingenious killers of the natural world. Killers that scuttle, slide, and slither. In this room, there are over 250 snakes, spiders, scorpions, and other venomous creatures. Their venoms have evolved over millions of years, and they're all different. The hope is that amongst this lot, there are some which could lead to a significant medical breakthrough. One of the greatest medical challenges is still cancer, particularly cancers of the brain. Brain tumours like this one here can be quite difficult to treat. If you use radiotherapy, chemotherapy, you risk damaging healthy tissue. If you can get at it and cut it out, then that's good, but also it's quite difficult sometimes to tell the difference between tumour and healthy tissue. Surgeons face a real dilemma in how much of the surrounding tissue they should remove.
Even though on a scan you may see a tumor that looks, let's say, 2 centimeters in size, we know that there are tumor cells several centimeters away from that ball of tumor. So to entirely remove everything, you would really need to be able to remove all that surrounding tissue, most of which is normal brain.
Removing healthy brain tissue could mean the difference between walking and not walking, seeing and not seeing, talking or being mute. And so being able to pinpoint unhealthy tissue is critical, which is where venomous animals may be able to help.
This is Lirius quinquestriatus, also known as the death stalker. As her name implies, she is a particularly venomous scorpion. A single sting from that tail could probably kill a child or an elderly person. And although probably not kill me, it would certainly be excruciatingly painful.
The venom of this scorpion contains a powerful cocktail of neurotoxins, chemicals that poison brain cells and nerve cells. One is called chlorotoxin. Chlorotoxin affects the nervous system of insects, utterly paralyzing them. But when trialed in human tissue, it did something completely different. It seemed to have a special affinity for cancer cells.
The compound bound to the tumor and avidly bound. In other words, once it's stuck, it stayed stuck.
Chlorotoxins from the scorpion venom bind tightly to receptor sites on the surface of the cancer cells. These are called annexin A2. Unfortunately, the chlorotoxin is not strong enough to actually kill the cancer cell.
However, when it's mixed with a fluorescent dye, it highlights cancer cells, allowing surgeons to avoid cutting out healthy brain tissue.
It can be visually extremely difficult to differentiate tumor from normal brain. They look alike, they can feel alike. So the ability to fluorescently identify areas that are abnormal based on the fact that they bind chlorotoxin and then remove that tissue is extremely appealing. So in the operating room, we would simply switch our imaging system to a system that shines infrared light and just look at the picture that we see. The areas that light up blue should be just tumor. So you can detect microscopic amounts of tumor.
It's promising research, and just one area where this venom could offer medical benefit.
Been a long process in development, lots of twists and turns, but I'm looking forward to where the future goes with this. It certainly has the potential to be very, very promising.
Animals produce a huge range of different venoms, and many have been shown to have remarkable properties. Venom from snakes has led to the production of a new type of antihypertensive drug for treating high blood pressure, while the lethal cone snail has produced one of the world's most powerful painkillers.
So who knows what other medicines might be lurking in the fangs of the creatures behind me.
Venoms are particularly appealing to modern researchers because they tend to be very specific. They seek out precise targets, which ties in well with another medical revolution that's going on. It too builds on the idea of targeting, but this time it's targeting at a genetic level. Medicine is getting truly personal.
The trouble with dishing out the same drugs to everyone is that we are all different. A drug that lowers my blood pressure might have absolutely no effect on yours. So how close are we to creating truly personalized medicines?
What we've found as we've sequenced the genes of a number of people is that everybody has slight variations and subtle changes in their genes, and these dictate ever so slightly subtle differences in the ways that cells respond to drugs. The concept is that we use that information to
Okay, and we can pause here. So this was our foray into diseases, non-infectious diseases. So We've been primarily looking at infectious diseases. We haven't been looking at the issues such as cancer, as well as the evolution of our next subject that we're going to be dealing with, or the subject we'll eventually be dealing with, biological warfare, okay, or in other words, weaponizing diseases. So very good, we'll end here.